Hi, everyone. These are the video recordings for Lecture 5 of Privacy in Machine Learning and Statistics. Today, we're going to cover three topics. First, we'll talk about some of the general properties that differential privacy satisfies that are really useful for designing and thinking about more complicated differentially private algorithms. We'll illustrate some of these properties in the design of a differentially private version of a popular clustering algorithm called Lloyd's algorithm. That'll be part 2. Then part 3, I'll talk a little bit about what the meaning of differential privacy is and what the right interpretation one should give to these definitions, the kind of definitions we're talking about in this class. Okay, so first let's talk about composition. So composition is sort of a general term that really encompasses two different kinds of things. And so, maybe it's helpful to think in your mind about two different scenarios. In scenario 1, we've got a person, Alice, and her data is actually in two data sets. So there's data set X1, and that's, this is her record here. And data set X1 is held by some hospital. Let's call it Hospital 1. And Hospital 1 is going to publish some stuff about its data. Okay, so we'll call that the output from Hospital 1. We'll call it little a1, and big A1 is the algorithm it's using to produce that output. But then there's another data set. Okay, there's another data set X2 that also contains Alice's record, let's say over here. And X2 might contain different parts of Alice's record. Based on, because maybe this, this data set is held by some other hospital and it has different information in it. But in any case, this hospital will also, Hospital 2 will also go and publish information, A2. And the question is, what is revealed by these two things together? So that's our first scenario. Our second scenario is that we've got, one data set, X, that is used in two parts of a complicated algorithm. So let's say that X is fed into A1, and A1 produces some output. Okay, so maybe, so think, that A1 are statistics on, blood pressure and diabetes in the data set. Like how many people have blood pressure, high blood pressure, how many people have diabetes, whereas, maybe A2 is now some second part of the algorithm. And what the interesting thing is that what happens if A2 somehow depends on the output of A1. So maybe A2 is going to be about either something about like blood pressure and diabetes together, or maybe if the result comes out differently from A1, it'll produce, A2 will be about some other thing, maybe heart disease. Okay, so the exact type of dependency doesn't matter, but the picture you should have in your mind is something like this, that the output of A1 is used to select an algorithm A2, and A2 is going to be run on the same data set X to produce an output A2. And again, the question is, what is revealed by A1 and A2 together? And actually, in both of these, what we can we can do is really think about the larger process that's going on as sort of a single big algorithm. So in run on a single big data set. So in this case, we're going to think of, the hospitals together as running one big algorithm A, which consists of both algorithms run by the hospital separately. Or alternatively, in this second picture, we'll think of, a big algorithm A that encompasses both the executions of A1 and A2 and the logic that goes into selecting A2 based on A1. Even if that logic is not like programmed out, it could just be a person making that decision. Okay, it doesn't have to be an actual, it doesn't matter for this discussion whether or not the decision of which A2 to run based on the outcome from A1, it doesn't matter if that decision is done by a human or by a piece of code or some other process. The only thing we're going to use the only thing we're really going to take advantage of is that the choice of A2 depends on A1, but it doesn't directly depend on X. The person selecting A2 doesn't go first look at the data set and think about and make a decision based on the data, but just based on the output from A1. Okay, and so it turns out these are actually both special cases of the same thing, and basically scenario 2 is the right picture to have in mind. And if it's not clear why that is, that turns out you can also view the joint data set X1 and 2 as one big data set X, which is the union of X1 and X2. Okay, so both of these scenarios are cases of composition. We can think of them as both basically being captured by this scenario 2, where one data set in the scenario 1, that's the union of the data sets held by the two hospitals, is first processed by one algorithm, and then a second algorithm is selected based on the outcome of that first algorithm. Okay. So let's try to set that up a little more formally. So suppose that A1 takes a data set in some universe and produces an output, and suppose that it is epsilon1 differentially private. And A2 is a data, it takes actually two inputs. So it takes an input, it takes the output of algorithm 1. So it takes an input in the set Y1 and a data set. And it produces an element of Y2. So these are both randomized algorithms, and the requirement on the second one is a little stronger than just differential privacy. So it should satisfy the following. It should satisfy that for every output I might see from the first algorithm, the algorithm I get by fixing that first argument to A2 and thinking of it just thinking of A2 as now as an algorithm that only takes a data set as input. This thing is epsilon2 differentially private. So these are my assumptions. First, that A1 is differentially private. And secondly, that A2 is differentially private no matter what the outcome from A1 is. So the behavior of A2 can depend on A1, but whatever that is, it should be differentially private. Then the joint algorithm. So we'll call it the following joint algorithm, where what we do is we first run A1 and then run A2 on A1 and X, and then return the pair. Okay, so this algorithm is itself differentially private, and its privacy parameter is at most, it's like the kind of loss of privacy, the degree to which it satisfies differential privacy is bounded by epsilon1 plus epsilon 2. Might be better than that, but it's never worse than epsilon 1 plus epsilon 2. Okay, so we're going to call this the composition lemma. And it's a super useful tool. Okay. In particular, what this tells us is the kinds of problems we saw with the hospitals example in last lecture are not going to come up with differential privacy. All right, so let's prove this. Well, let's fix neighboring data sets. X prime. So what we want to show is that, recall what we want to show is that for all events in Y in the output space, which in this case is like the product of Y1 and Y2, the probability that A of X lies in E is at most E to the epsilon 1 plus epsilon 2 times the probability that A of X prime lies in E. And what we saw last time is it's sufficient to look at one output at a time. Okay, so it's sufficient to show this condition, not for like some arbitrary complicated set of outputs, but just at a single, we only have to look at one output at a time. One pair A1, A2. So let's fix our favorite. So let's fix our favorite pair of outputs A1, A2. And now the probability that algorithm A produces this pair is going to be at most, it's going to be exactly a product of two things. So first of all, it's the probability that A1 of X produces A1 times the probability that A2 of X produces, A2 of A1 and X produces this little A2. Okay. And I just want to point out that in this expression, like, because we're looking at the probability of a particular pair A1 and A2 on a particular data set, none of these things are random. The only randomness that's left, okay, so these things in blue, they're all fixed here. The only randomness is over the coins, the random coins of the random choices made by A1 and A2. All right. And we can write, because we've conditioned on A1 effectively, we've like fixed A1, that allows us to break this this event into a product of two separate probabilities. All right, now we can bound each one individually using what we know. So we know that the first algorithm is epsilon 1 differentially private. So there we've got the probability that A1 of X is equal to little A1 of X prime. Little A1 is, so it's at most E to the epsilon 1 times that, times E to the epsilon 2 times the probability that algorithm A2 run on input, again on little A1, but now on data set X prime, produces A2. And so notice that the only thing that's changed in the A1 part is the same in both expressions, in both lines of the equation inequality, but the data set, only the data set has changed between these two lines. And now this, this we can recognize if we pull out the E to the epsilon 2 up front, then what's left is a product of two probabilities involving X prime, and that's exactly the probability that the algorithm A on input X prime would produce the input we want. So this is exactly E to the epsilon 1 plus epsilon 2 times the probability that A on input X prime would produce a pair A1 and A2. So that concludes the proof. So that's what we needed to prove. We're done. Okay, and so why is this useful? Well, what it tells us is that, again, when we run two algorithms together, their privacy loss accumulates. It can degrade. I mean, it's worse than running just either of them individually, but it degrades in this kind of graceful way. And by induction, we can get a similar statement for the composition, the adaptive composition of any set of K algorithms. A1, A2, up to AK. Again, where the choice of each algorithm, let's say AI, can depend on the outputs of A1 through A-1. So it is, this whole thing is epsilon differentially private for epsilon, which is the sum of the parameters of the individual algorithms. So AI, this is under assumption that AI is epsilon I differentially private. Okay. So this is sort of the main principle we're going to use, that we can compose together sequences of algorithms in this way. And so you could sort of extend the picture that's up here, this picture here, but with more pieces. So you could have A3, A4, A5, and again, the privacy loss degrades in a nice, smooth way. Okay. So a consequence of all of this is sort of we can think of our privacy parameter as a sort of budget that can be allocated into pieces among the different components of our algorithm. Okay, so we can think of our privacy parameter epsilon as a budget to be allocated among pieces. And that's often a really useful kind of mental metaphor to have. Although one of the exercises we'll do in class is sort of thinking about when that's not quite the right mental model, but generally thinking of the privacy parameter as a budget to be divided, that is a useful way to think about things. All right. So another useful property that differential privacy satisfies is called postprocessing. Okay, so here you should have the following picture. Suppose that we've got an algorithm A that's differentially private. It produces A1, and it is fed through some, other process B that leads to an output little b. Okay, so the question it's often convenient to sort of think about, to design algorithms or phrase algorithms as sort of, there's this one big algorithm, let's call it A prime, which is the composition of B and A, where I don't really know much about B, but I know that A is epsilon differentially private. Okay, so a useful lemma is that if A is epsilon dp, then so is A prime. A prime, which is the composition of B. So A prime, it's the composition of B applied to A, regardless of B. Okay, so I don't need to know much about the structure of B. One thing that I guess I do need to know is that B is not directly reading the input X. It's just using it. All it has access to is the output of A. Okay, so let's just prove that. It helps to first think of what happens. So let's first prove look at what happens when B is just a deterministic function. Okay, so then the probability that B of A of X lies in some event E, that's equal to the probability that A of X satisfies, it lies in the set B inverse of E. Okay, and here, let's just move that over to make space. B inverse of E is the preimage of E. So it's the set. So B inverse of E is the set of values A such that B of A lies in E. Okay. And so the probability that the composed algorithm produces an output in E, that's just the probability that A's output lies in some specific set. And so by differential privacy, that's at most E the epsilon times the probability that A of some other neighboring data set X prime lies in that set. If this is assuming X and X prime are neighbors. And then this is just equal to E to the epsilon times the probability that the composed algorithm on input X prime produces output in E. And this argument works for all X prime, and E. Okay, so it's suffices to prove that B composed with A is differentially private. We're not quite done. Let's look at what happens when B is randomized is itself some kind of randomized process that's not just a deterministic function. Okay, and it's still the case that we can then sort of basically reduce to the case of deterministic functions. And the idea is that we can write the execution of B on input A as some deterministic function F applied to A and some like randomness R. So here F is deterministic and R is a random variable that's independent of A and X and everything else. So R is just like the random choices made by the algorithm B. And so we can actually just apply, so we can really apply our previous reasoning to just to the function F. Okay, so first let's consider an algorithm A double prime of X that produces A of X and also generates a sample from the random coins R. That's also epsilon differentially private, just because all it's doing is running A and then appending a bunch of like independent stuff. If you want, you can think of this as a special case of composition, although it's certainly simpler than that. And now the algorithm we really want to think about, B of A of X, that is just F applied to A of X R. And so what we're doing is we're applying a deterministic function to the output of an epsilon differentially private algorithm. So this thing is epsilon differentially private by the first case. Okay, case one, let's call this case one. Case one and case two. Okay, so QED, we're done. Okay, so post-processing is also useful because, again, sometimes, sorry, you should have this picture in mind that often we'll express some process we want to think of as first running some differentially private algorithm and then doing stuff to the output. And that doing stuff, it doesn't really matter how complicated it is. It doesn't affect the differential privacy guarantee. It doesn't make it any worse. It might make it better, but never will make it worse. All right, so those are the first two properties. We saw composition and post-processing. And the third one is called, the third one we'll talk about in this part of the lecture, is called group privacy. And here, you might ask, like, what happens if what I care about is not like what's revealed about just Alice, but like Alice and her family, you know, like a small group of people. Okay, so it turns out that differential privacy has the privacy guarantee degrades a little bit as you increase the set of people that you're asking about, and that makes sense. But it degrades in this pretty smooth and graceful way. Okay, so let's look at the following. So, you know, the question we're asking is what's revealed about a group of, let's say, k people for some integer k, you know, greater or equal to 1. Okay, so here's our lemma. If we've got two data sets, x and x prime, that differ not in one record, but rather in k records, then for all events E in the output space, if A is epsilon differentially private, and forgot that. Okay, so if A is differentially private, x and x prime differ in k records, then for all E in the events E in the output space, the probability that A of x lies in E is at most E the epsilon times k times the probability that A of x prime lies in E. Okay, so what are we picking up? We're picking up this like extra factor of k in the exponent. So the privacy parameter is getting blown up by a factor of k when we look at a group of size k. Or by, I guess one should say the privacy parameter is blown up by a factor of at most k when we look at a group of size k. Could be better than that. Again, that depends on the specifics, but it's never worse than this factor of k. Okay, so the boundaries of this lemma got a little hard to tell, so let me just. All right. All right, so what, you know, proof. Okay, let's just prove that. What's the picture you should have in mind? Here's x, here's x prime, and they agree on a bunch of records, but then there's sort of k records where they disagree. These guys differ. So what we're going to do is imagine a chain of intermediate data sets. Okay, so maybe we'll make these the red records, and these ones over here, the blue records. We're going to consider a chain of intermediate data sets, like x1, x2. We'll call the original x, we can call it x naught. So these are all data sets. And maybe I'll, just so that you don't get confused with data records, I'll call this x naught, this one x1, x2, all the way up to x of k minus 1. And we'll just imagine like changing one record at a time. So this first data set, x1, will have mostly red records, but one blue record. And the second data set will have 2 blue records. And the rest will be red. And then the last data set will have k-1 blue records and only one red record. So it'll look something like this. You know, in the first data set, there'll be lots of red records, k-2 red records. By the time we get to step k-1, we've got one record left. And then at step k, so this is the same thing as xk, we've got k records. So if I look at the probability that a of x lies in some event e, well, that's at most e to the epsilon 1 times the probability that a of x1 lies in e. Okay, and so that's at most e to the epsilon 1 times, e to the epsilon, there's no epsilon 1, times e to the epsilon times the probability that a of x2 lies in e, because x and x2 are neighbors, right? So the point is every step in this chain, the adjacent pairs are neighbors. Okay, they only differ by one record. And so at each step in the chain, you're picking up a factor of e to the epsilon. So eventually we'll get to, you know, e to the epsilon times k-1 times the probability that a of x k-1 is in e, right? So, and then the final step will be like e to the epsilon times k times the probability that a of x prime, the thing we originally cared about, is in e. Okay, and that is enough to prove our lemma. Okay, so what have we proved? We've proven that if you take a group of k records, then the statement you can make about like what would be changed by replacing all of them with garbage or with some other record, you can say that the probability of any set of outcomes goes up by at most e to the epsilon k. Okay, so that's often useful when we're reasoning about, again, a small set of points. It also brings us to an interesting meta point. So it's sort of like a meta observation that is important here, is that if if two data sets, so let me rephrase that. You know, every pair of data sets, let's say like x and x tilde, they differ by at most n entries. Okay, like there's no way you can have two data sets of length n that differ in more than n entries. And so that means that the probability that a of x lies in E is at most the probability that a of x tilde lies in E times e to the epsilon n. So when epsilon is like much smaller than 1 over n, this really means that no information at all is revealed about anyone in the data set, but actually about the data set, no like useful information at all can be revealed. So maybe that should make us sad, because on one hand, it says like, well, if you crank this privacy parameter down really small, then like it's hard to tell apart like even totally different data sets. Like one data set where like everybody is, everybody has blue hair from some other data set where everybody has red hair. Okay. And so there's just like no useful statistics at all that you can reveal, because the probability distributions on your outputs for all data sets should be basically the same when epsilon n is small. So that makes us sad, but it also, like, there's a flip side to that, which is that, like, what we realize is, like, oh, what that's telling us is that there's really no way to reveal useful information without revealing a little tiny bit about everyone in the data set, or about many of the people in the data set. Okay, there's no way to get, like, the kind of security we get, say, in cryptography, where we get perfect encryption. If we make epsilon really small, then there's nothing useful to be said. If we make epsilon big, then indeed we can do useful things, but then we have to be it's like much trickier to reason about. We have to be very careful about, like, what exactly we're revealing, and that's the whole point of differential privacy. So we'll work in the regime where epsilon has to be bigger than 1 over n, and another consequence of that is that getting good differentially private algorithms that work with really tiny data sets, that's very hard. Like, it's much easier to satisfy privacy when you've got a big crowd that you can sort of hide in. Okay, so I will stop there for part 1.